Okay, good afternoon. Thanks for coming. I'm going to be doing a live demo today if the demo gods cooperate. So I'll do the best I can with the fonts. If you're in the back and you can't see, it's kind of a cozy group today, so feel free to come up if you have trouble seeing the slides. My name's Dan Marshall. I'm with Honeywell Aerospace. I'm the big data architect. And today's demonstration is showing how to do a simple data federation use case with Spark. So we're going to combine data from Postgres, HBase, Cassandra, and JSON to produce a data mart for a contrived use case. I'm going to do this presentation using the Zeppelin notebook. And let's see what we can do with the fonts. Let's go that way. So I've decided I don't have enough excitement in my life, so I wanted to do a live demo. So we'll see how exciting it gets. Here's the scenario. Imagine a user that has an employee table on Postgres, and they want it to be enriched with data that resides elsewhere. So in this case, there's some information in Cassandra, there's some information in HBase, and some other information sitting in a flat JSON file. And in this scenario, when I'm kind of loosely calling data federation the general idea that the data is someplace else. I don't want to move it. I don't want to do an ETL operation. I kind of want to leave it where it is and then produce some kind of a temporary result. We'll show that in Spark. And then also we'll persist it to an imaginary data mart that has all of the enriched data in it. We'll put that back into Postgres. The environment I'm using is all running on my laptop. I've got 3 Docker containers, one running Postgres, one running Cassandra, and one running the Hortonworks HTTP 2.6 version. And I think I'm going to sit down, make it easier to see. You'll notice in this demo I use cache a lot. I'm really doing that for the purpose of the demo. With this Docker configuration, I was getting some timeouts, so I use cache just to make sure I don't lose the data. But you probably wouldn't want to do that for this kind of a scenario in the real life. Cache is going to persist it in memory by default or on memory and or disk. So after I've done a result and created a data frame, I can cache it so that I don't have to go back to the source and get it again. So once I read it from Postgres, it's in my Spark environment, and I don't have to go back again. So the first thing I'll do is I'll read Postgres, that employee table that we're starting with, and I'll convert that into a data frame. And in this case, I'm doing what I'm calling a naive default JDBC non-parallel read. So we'll look at doing a JDBC read without worrying about parallelization. And then we'll show an example of how to exploit some of the Spark parallel capabilities. So I hope you can see, can you guys see that in the back? It's okay? Okay. So I'm using Spark 2. So this is the interpreter in Zeppelin. I'm issuing a SQL statement into this Postgres table. Actually, let's go look at the Postgres table. So this is the table. It's only got 4 rows for the demo, but you can imagine it has 4 million or 4 billion. But just for the purpose of the demo, it's just got 4. The table has an employee ID, an employee name, a title, a hire date, and a department ID. So this is what we're starting with. What the end users are looking for is enrichment so that they can get the name of the department, because this department ID isn't very useful. There's some bonuses that have been issued to some of these folks, so there's a separate bonus table. And then there's a table that talks about whether they're exempt or non-exempt. So this is what we're starting with. So to use the JDBC connector, which is what I'm using here for Postgres, we do a very conventional looking select statement. In this case, selecting from that table that I just showed you. Using the SQL context, I'm going to read that using JDBC, and I'm going to pass some options to it. If you've ever written JDBC code in Java or some other language, you know that you set up a connection with a series of parameters, connection URL, user ID, passwords, those kind of things. Those are being passed here as a map underneath the dot options. So here's the JDBC connection string to Postgres. There's the IP address of the server, port number, database, blah, blah, blah. The JDBC driver, the table, and the password. And then I do a dot load, and that's all it takes to take that table using that select statement and load it into a data frame. If I had a where clause up here, then I would just get that filtered selection in the data frame. I'm going to cache it, which we just talked about, putting it into memory in Spark. I'll do a show, and then I'll print the schema. So let's run that. And you can see this data should look familiar. So this is the same data that we just read out of Postgres. And now it's in Spark. It's in a data frame. It has been cached. Spark has picked up all the schema from the JDBC connection. So in a JDBC query, part of the interface is to deliver the schema of the result set. So the first step is kind of finished. But what's really happened here is we didn't do anything about parallelism. So the reality of this is, actually let me go back here and change this. I'm going to call this PG1A. So using the Spark UI, if I look for PG1A, you'll see here, or maybe you can't see it. What it's telling us is that there's one partition. So what happened is a single partition is being created by a single task. If this was a very large table, that's not very efficient. We haven't used any parallelism in Spark. So let's add some parameters to the JDBC connection. And what we're going to do is incorporate something called a lower bound and an upper bound. And I'll show you that this is not really related to filtering rows. So it almost sounds like, if you remember, a data set has keys 1, 2, 3, and 4. The upper bound and lower bound is not related to that key. It's more related to a suggestion to Spark on how to parallelize the query. And I'll show that in a second. So like I say, it's a suggestion. This will cause multiple SQL statements to be created. So instead of a single one that we just saw, if I specify something like 2 partitions, we'll get 2 separate SQL statements executed. One's probably going to say something like where employee ID is less than or equal to 2, and the other one might say something like employee ID greater than 2, right? So we'll get the right result set, and we'll go back into the answer. So the point here, it's always going to return all rows no matter what is entered for the lower bound, upper bound. So the difference here is now we've told Spark that the partition column is employee ID. The number of partitions is 2. We have a small data set. The lower bound is 1 and the upper bound is 4. So I know something about this data. I've said that. And it should work pretty well. So let's try, I'm going to call that 3A. I'm just renaming it so they can find it easier in the interface. Okay, so that's finished. So if we go back to our storage, look for 3A. Now we see number of partitions 2, right? So we've had the same result, ran the same SQL query. Now we parallelized it to 2 partitions in Spark. But let's say we didn't know the data very well. Whoops. Sorry, I'm trying to get back to where I was. Oh. So I'm going to put number of partitions 12. I'm going to say the upper bound is 10, or the lower bound is 10, and the upper bound is 400. Now, based on what I said, we should see the same answer that we got before, and we do. So again, lower bound, upper bound, nothing to do with filtering rows. It's just a way to influence the optimizer. So now if we go over to storage and look at PG3, I should have renamed it, but we'll call it that anyway. Might be another one. Did I actually run it? Let's call it something else. Not sure why it's not showing up. It might be a lag. Let's see. Aren't live demos fun? Ah, there it is. So now you can see number of partitions 12. So what's actually happened, if you look at all these executors, so there's 12 of them, only one of them looks like it actually did any work. So I did 12 SQL statements, one of them returned all the rows, and 11 returned 0 rows. So if you're using a JDBC data source and you want to make sure you parallelize it, make sure you understand your data. Do a simple min-max account, and then you can get a much better idea how to do this. All right? This is going to work best when you're using something like a primary key. And of course, if it's evenly distributed, it's going to give you much better parallelism. If you have a lot of skew in the data, it's going to do its best, but some of the partitions might be skewed. So we've got Postgres read into Spark and cached. The next thing we'll do is look at HBase. And by the way, if you're ever doing a demo in Zeppelin like I'm doing now, when I increase the font, you'll notice that really that annoying top part just keeps getting bigger. So there is a JIRA ticket open to allow you to hide this or roll it up, and that's coming. So this HBase, I use something called the new API Hadoop RDD, which is not so new anymore. And we'll show a newer alternative here. There is something that's come out recently called the Apache Spark Apache HBase connector from Hortonworks. The GitHub site is here. And that's a much richer kind of HBase interface than I was showing you today. It does some nice push-down optimizations, data locality, partition pruning. It also provides capability to have Avro schemas. So if you're storing your HBase data like you typically would as an array of bytes, or if your Avro record is an array of bytes, you can get some help serializing and deserializing that during the queries, which is pretty neat. But for now, we're going to use the new old API. We bring in some standard imports here. This is just some boilerplate stuff for connections to Zookeeper. The table name we have here is table name, and we have a column family 1 with the department name. So let's go look at what's in the HBase table. And I have a confession to make. I cheated. HBase has been taking all the memory from the Docker, so before this demo started, I ran the HBase part, and I've already cached it in Spark. So just imagine I'm running this now. Wow, that was fast. So there's the HBase data. There's 3 rows in this table. The row keys are F1, M1, and S2, which should look familiar because they match our initial data set. And here we have some values: entertainment, maintenance, and sports. So basically, we're going to pick up the department name from HBase for our enriched employee table. So if I go back to Spark, I'm not going to hit run, because if I do, it's going to say I can't find it. So again, suspend belief for a while, and this is the result. So it comes back with an array of code, department name, et cetera, et cetera. It picks up the schema, and now we've cached our HBase results. So now we've got Postgres cached, and we've got HBase cached as data frames. Now we're going to go ahead and join these, and I'm doing this stepwise. In reality, you could just do a 4-way join when you're done, but I'm trying to step through this demo. So we're going to join the Postgres table that we started with HBase. In this case, we're using kind of a DSL style join using Scala. And we're going to show how we can do things like rename, drop columns. In this case, I'm going to drop the redundant columns from the join, because we'll pick up the employee ID from both tables. And here's what it looked like. So if you're used to SQL, this is a little bit different, but it's the same general concepts. I'm going to create a new data frame called add department name. I'm going to take that Postgres data frame from up above. I'm going to join it with the HBase data frame. These are the columns from each side of the join. It's going to be in left outer join, so we don't drop anything out of the Postgres table. And then because this employee department ID is redundant, I'm just going to drop it at the end after I create the data frame. So when this is created, it will only have one department ID in it. It's pretty standard. I'm going to cache it, and then I'm going to show it. So I think it's safe to run this. And now you can see that we're starting to enrich the table. So we've added another column, the department name, based on the join on the employee ID. Or I guess it was the department ID, whatever it was. So I've created another data frame in Spark based on 2 cached data frames from Postgres and HBase. So let's keep moving. So the next thing I'm going to do is look at Cassandra. And that has information about bonuses for the employees. And I want to bring those into this also. So in this, I'm going to show a couple other things that aren't really related to Cassandra, but I wanted to bring them up during the demo. One is we're going to show the use of create or replace temp view, which is new in Spark 2. Previous to Spark 2, you would have used register temp table. So it's just the idea of registering a table during your Spark context that's a result of some kind of an operation, a data frame. There are ways to persist it to Hive if you want to do that, but that's not what this does. This just keeps it active in memory so that you can reference it as SQL or using SQL. We're going to show how you can create both a data frame and a data set. And we'll talk about how a data frame is just a special form of a data set. In the data frame, we're going to cache the data type. We're going to do some renaming of columns. I talked about that. The other thing I'll mention is that Spark Cassandra is a very rich connector. It has some interesting things like join with Cassandra table. So Cassandra has the concept of a partition as well, but it's different use of the same term. It doesn't mean the same thing as a Spark partition. But there are ways using this connector, if you know your data well enough, to even do co-location depending on your hardware setup, or at least join or associate Cassandra partitions, which are based on the key, with Spark partitions. So you can do some real nice parallelism both on Cassandra and in Spark. In my demo today, I'm just going to read the whole table because it's only got 4 rows in it, or 2 rows. But if you want to learn more about that connector, there's a GitHub project listed here. And everything I'm showing you today will be in the slides, so if you want these URLs, they'll be available when you download it. So let's run that. Actually, let's go look at Cassandra first. So here's the bonus table. Only 2 employees got bonuses. Sound familiar? Only 2 employees got bonuses. User ID 1 got 500, user ID 4 got 1,000. The other 2 did not get a bonus, so they're not in the table. So let's go run this Cassandra. Actually, let's look at it first. So in this case, the read format, we're bringing in this driver from Cassandra, which is, you can download. And by the way, if you haven't used Zeppelin before, all these kind of dependencies and jar files, you can put them in your interpreter configuration so that they're available. And you can even give a name like this, and it'll go out to Maven Central and grab it for you if it's not already cached on your machine. Or if you have a repository behind the firewall like Nexus or Artifactory, you can get it from there, obviously. So you can configure all that in your Zeppelin. Similar to if you're using Spark Shell, where you list the jars in the command line, it's the same idea. So here we're giving some options to Cassandra. This is not JDBC. This is specific to Cassandra, but it's also passing options as a map. So it's just key value pairs. The key space, as you saw in the query, was my key space. It's called bonus table. The Cassandra host is at this IP address. I'm loading it. And then I'm adding this extra step here to create a temporary view called bonus table. So everything up until the load, you can think of as just the Cassandra piece. And then at that point, I have a data frame. So this last piece is just applying to that data frame I've created as part of this statement. And I'm just doing this to show that how I can access bonus table later using SQL, just for giggles. I've also showing a case class here called good. So think of this as a domain object. And we're going to use this to create a data set. And a data set distinguishes itself from a data frame because of strong typing. And we'll look at that. So if I say on this statement, data frame equals select star from bonus table, I'm going to create a data frame called CastDF. I'm also creating a data frame called CastDF2. And I'm renaming the column to bonus amount and employee bonus. So the end user who wanted this data mart didn't like the name bonus amount, so they wanted it changed to employee bonus. So as part of a data federation operation, it's nice that you can kind of rename these things on the fly. And you can see that it's relatively easy to do. What I'm doing here on this statement that says CastDS for data set is I've applied as good. So when I create that result, I'm applying this case class to it. And the case class is just a Scala way of kind of applying a structure to something. So like a record format almost. By doing that, this object will be a data set as opposed to a data frame. This will be a data frame. And a data frame is really just a data set where the type is the generic row object. So a data set, in this case, might be something tangible like a bottle or a mouse or an employee or something like that. It's some domain object, and it's going to do strong type checking. So if you do something like select something that doesn't exist from it, you'll get compile time errors if you were doing development and compiling things. If you're using a data frame and you said select non-existent column from table, you wouldn't find out till runtime that you'd put in a bad column name. So if you're a developer, you're going to care more about data sets if you're writing Java Scala code, if you care about things like typing, strong typing. So let's run that and see if anything happens. So now this is actually going out to the Cassandra Docker across town and pulling in some data on the other side of my hard disk. So the results came back as those same two users that we saw when we looked at the CSQL query earlier. If I look at the data set, and this has nothing to do with data sets or data frames, I just wanted to show you how you could kind of clean up the data as part of a federation task. If I did nothing to it, it shows up as a decimal field 3818. So it took the maximum precision and the maximum scale, and it gives you kind of an ugly looking result like that. But in the case of the data frame, you'll see something that's a little more human readable. That's because up above I did this. So you can see I cast the decimal type 7,2. So basically I took this bonus amount, I cast it to something more readable, then I also renamed it. So you can kind of string these things along as part of the data frame. And you don't really need to be a developer to do this kind of thing. It's pretty intuitive, right? It's sort of a nice DSL. If you're thinking about using Spark and you don't know Scala, don't let that scare you. Just think of this as Spark commands. They happen to be Scala, right? You don't need to learn the Scala language to start writing Spark code. So now we've got Cassandra cached in Spark also. I'm going to take a little side detour here, and I'm going to just run a query in Zeppelin against this Cassandra table. And I'm trying to scroll. Anyway, I'm using the built-in visualization as part of Zeppelin. So this bonus table is really a Cassandra table. So the point here is that you could have a table sitting in Cassandra, you could fire up Zeppelin, and you could start writing queries, which is kind of nice. And it's not that hard. And this is a fascinating graphic, so I'll let you, isn't that something? But there's, you know, if you've seen some of the Zeppelin stuff, it can get pretty exciting. Okay, now I'm going to come back to the federated example. I'm going to join the Cassandra table to that latest version of the employee table that we had. And I'm going to add the bonus information. The Cassandra source only has employees receiving bonuses. In this case, just for the purpose of the demo, I'm going to switch and I'm going to use a SQL style join instead of that Scala join that we saw earlier. And even though we're doing that, we can still do the same kind of enhancements. In this case, I'll show how to replace the missing null bonuses with a 0. And I talked a little bit about that partition thing already. So let's try this. So now this join, you see if you're a SQL person or you're more comfortable with SQL, this should look very familiar, right? This is a SQL join that you would see in any dialect. And it's just an alternative way of doing what we did earlier with the ... Again, because it's a data frame at this point, we're dropping the user ID. I'm renaming, applying a coalesce to this employee bonus. And coalesce works just like it does in SQL. It takes the first non-null value you put here. So if the employee bonus is null, it's going to put a literal 0.0 into result set. And down below, this commented out one is just the alternative version if you wanted to see them side by side. So this is the SQL version, and this is kind of the Scala version. So let's run this. And now you can see the employee bonus has been added to the table. So we're starting to build, we're starting to enrich this table. Now it's got Postgres, HBase, and Cassandra in it. And you've also got zeros here instead of nulls. Are there any Scala programmers in the room? I'm not using nulls. See, he's happy. Yeah. If you use nulls around Scala, they just kind of dismiss you. You don't know what you're doing. Nulls are so 1990s. So that takes care of that. The next thing we're going to do is imagine we've got a JSON flat file that has information about whether a department is exempt or non-exempt. We're going to copy that to HDFS, and then we're going to suck that in as another data frame and use that to further enhance the data set. This is the shell interpreter, which Zeppelin supports sometimes. It's been crashing lately. But basically, it opens up a shell command and kind of arbitrarily lets you type in shell commands. In this case, I'm doing a copying from the local file system into HDFS. And here's the result. This is what the very simple JSON file looks like. So it's got a key value pair, department F1, department S2. So what this means is that these two are both exempt departments. If you're not in this table, then you must be non-exempt. So let's read that JSON file and put it into a data frame. And what we're going to do a little bit different with this one is because, remember we're imagining that these other data sets are big, they have 4 million instead of 4 rows. This one might actually be a very small file. So imagine a company is not going to have that many departments. This will easily fit in memory. So what we're going to do is we're going to broadcast this across all the executors in Spark. So it's going to be local on every executor. And you can see here where it tells us that that broadcast happened. And the way you make that happen is right here. So you take the Spark context.broadcast. So at this point, if I do read.json and I pass it a JSON file, Spark knows how to read JSONs very well. JSON's a well understood format. It'll infer the schema from the key names, and we're going to broadcast it to all the executors. So what that means is that when the join we're about to do happens, it can do a map side join to the table. So it doesn't have to do shuffling and all that kind of hoo-ha. The data is going to be local, and it can just take the department ID and do an in-memory map to find out whether it's exempt or not. So now we're going to join the federated employee table with the data from JSON to enrich the table with the exempt status. This will create our final table. And then we're going to show an alternative way to replace those missing nulls. And we're going to actually create a Boolean column. So we're going to create a new data type on the fly. Let's just run that. And this is the point in the demo where something weird happens. JSON, oh, did I not run the JSON file? Maybe I didn't run it. No, I definitely ran it there. So let's try it again. I did pray to the demo gods this morning when I woke up, so far so good. So now I'm creating the final table. I've taken that add bonus data frame that I had cached. joining it with the JSON data frame on department. Again, left outer join. The exempt department. Now in this case, you can see something that starts to look like a little bit like logic. So when the value of the department is null, false, otherwise true, drop. So coalesce this, you can do the same thing a couple different ways, and there's a lot of different options. Because this is just Scala code, you can write your own functions to do things at this point. And no nulls. You saw that? Yeah. Okay. I'm going to cache the final table, and I'm just going to create a enriched employee table as a temporary view so that we can do some SQL on it. Here's the whole table. You notice the last column, exempt, is a Boolean, so that's either false or true. So there was no false or true in the data set that we joined it with, but we used Scala to kind of materialize that Boolean column with the right value. So in this case, Fred Flintstone is exempt and everybody else is, or he's not exempt, everybody else is exempt. So now that I've got this temporary view in Zeppelin, I can do some more amazing graphics like this pie chart that shows the percentage of people and what department they're in. So at this point, if I was doing data federation and I was just kind of a Spark analyst, I could kind of stop here and do whatever I want with that enriched table, right? We haven't moved the data anywhere except into our context. When this job is over, we haven't saved anything, right? So it's a true federation in the way I described it earlier, where we're not moving the data, we're just leaving it in place. Now, in this particular example, the end users wanted us to put it back into Postgres, because they don't know this Spark big data stuff. I don't know what all that means. I just want my relational database. So we're going to put it back in Postgres for them. We're going to use overwrite mode. So every time we run this, we're going to create a new Postgres table with the enriched information in it. It's going to create the table if it's not present. That's configurable. We have the same issue with number of partitions. So remember, back at the beginning, we talked about influencing the number of partitions used during a read. You can do the same thing on the insert. So you want to make sure you don't overwhelm the receiving database, in this case, Postgres. So what you usually want to do is probably reduce the number of partitions than the default that Spark would give you. So imagine this was in 2,000 partitions. You don't want 2,000 connections to Postgres, right? You become very unpopular with the DBAs. So you need to kind of coalesce that down. So you literally do a coalesce, but it's done under the covers based on this number of partitions parameter. So it's the same term used for reading, we're doing it for writing. There are some cases where you might want to increase that, and in that case you would do a repartition, which would be a lot more inefficient than a coalesce. A coalesce kind of happens on the same executor, so it's a little bit more efficient. And generally on the inserts, you've created this large thing, you want to put it back into JDBC. You want to get the number of connections down to a reasonable number so you don't overwhelm the target. So what that looks like is, instead of a read.format JDBC, it's write.format JDBC. Again, you can specify the mode. It could be append. In this case, I'm doing overwrite. There's the table again, passing options. And in this case, instead of a map, I'm just showing you how you can do it with a dot option also, but it's the same thing. You're passing key value pairs to the JDBC API. I'm saying number of partitions 2. I'm doing a save. And just to prove I'm not making this up, we can go over to Postgres. So the employee enriched table has 0 rows in it. And now I'm going to run this. And if I go back, it's got the enriched data, and including the exempt Boolean column and all the rest of it. So now our end user is happy. They've got an enriched data table, and every time this runs, we'll just replace it. And it's 450. So that's all I had. Any questions? Comments, corrections? Yeah. The Scala guy, yeah. Cannot use a what?
Does it have the same limitation where you cannot use a date time field?
Yeah, the question was, this is similar to scoop. Does it have the same limitation that you can't use date time? The last time I checked, it has to be an integer, right? I think there's some work being done to allow other data types, but I believe today it's still an integer required. So you could, I suppose you could hash it to an integer and do some monkey business, but yeah. Anything else? Okay, we're out of time, thanks.